To most people, this looks like chaos, curves, circles, nothing straight. And somehow, engineers use it to build wireless systems that actually work. But for an RF engineer, this is not chaos. This is a map. This is the Smith chart, and it's one of the cleanest ways we have to tame the chaos of physics. In this video, I'll show you what it really represents, why it exists, and how engineers actually use it, without drowning you in math. At low frequencies, we often pretend circuits are simple. Wires are just wires. A resistor is just a resistor. But at RF, that assumption breaks down. RF signals don't behave like static voltages. They behave like waves traveling through space and along transmission lines. When a traveling wave reaches the end of a line, it expects to see a certain impedance. If the load matches that impedance, the energy is absorbed. But if it doesn't, part of that energy is reflected back toward the source. If part of the signal goes forward and part of it comes back, engineers need a way to measure that reflection. Not with guesswork, but with a single precise quantity. That quantity is called the reflection coefficient. It tells us how much of the signal is reflected and how much continues forward. A small reflection means most of the energy is delivered. A large reflection means most of it comes back. When there's no reflection, the reflection coefficient is 0. When everything reflects, it reaches its maximum. Every real RF system lives somewhere in between. The reflection coefficient isn't just a number, it has magnitude and phase. And that's exactly why we need the Smith chart. Our first instinct is to use a normal graph. Resistance on one axis, reactance on the other, and mathematically, that works. But RF doesn't stay nicely inside a box. As frequency changes, reactance can grow without bound. The graph keeps going, the picture breaks. There's another problem. In RF, impedance changes not just with components, but with distance and frequency. A single point isn't enough. This is the insight that changed everything. Instead of letting the graph run off to infinity, what if we folded it into a finite, readable space? That's why the Smith chart exists. The Smith chart didn't come from simulation software. It was created at a time when engineers had slide rules, graph paper, and real hardware on the bench. They needed answers fast. In the late 1930s, Philip H. Smith introduced a new way to visualize impedance and reflections. Not new physics, a better way to see it. What's remarkable isn't when it was invented. It's that even today, like with powerful computers and simulation, the Smith chart is still everywhere. Because it turns equations into intuition. Let's break the Smith chart down. Start with the horizontal line across the center. Every point on this line represents pure resistance. No capacitance, no inductance. The exact center of the chart is the point engineers aim for. When impedance is normalized, this point represents a perfect match. Above the center line, the impedance behaves inductively. If your point lives up here, your circuit looks like a coil. Below the center line, the impedance behaves capacitively. Down here, the circuit looks like a capacitor. Here's where the Smith chart really comes alive. At RF, impedance is not fixed in space. It depends on where you are along the transmission line. As you move along the line toward the generator or toward the load, the impedance doesn't change randomly. It rotates. This rotation isn't about meters or feet. It's about electrical length. How many degrees of phase the wave accumulates as it travels. So when engineers move a probe, change a cable length, or trim an antenna, they're not guessing. They're watching the impedance rotate in real time. And once you understand rotation, impedance matching stops being guesswork. It becomes navigation. Let's say your antenna doesn't land at the center. That means some of your power is being reflected back. Higher VSWR, less range, more heat. Here's the trick. When you add a capacitor or an inductor, you don't change the circuit abstractly. You move the impedance point along a predictable path. Add the right value, and the point lands right here. Maximum power transfer, minimum reflection. This isn't theory. This is exactly what engineers see on a network analyzer while tuning real hardware. The Smith chart turns tuning into navigation. The Smith chart isn't complicated, it's just unfamiliar. Once you see it as a map instead of a math problem, everything starts to make sense. Every antenna, every RF amplifier, every matching network, they all obey this chart. If you understand it, you stop guessing, and start designing. In the next video, we'll take this chart off the screen and onto real hardware. We'll use it to tune an actual antenna and build a matching network step by step. If this helped you see RF differently, subscribe to RF101 Explained. This channel is about turning radio frequency into intuition. I'll see you in the next video.